Okay. So one issue that I told you earlier is deadlock that this deterministic routing eliminates. I'll briefly cover what it is because people have worked on this a lot actually, and it's interesting, and it appears mainly in buffered networks, and this is one downside of a buffered network. Deadlock is no forward progress because you have circular dependencies on resources. You get deadlock, and in this case, each packet waits for a buffer occupied by another packet downstream. So if you look at this, this is a router, and these are buffers, and this is the input selection circuit, if you will, and this is the packet progression. This packet needs to, this packet 3 needs to go here, but that buffer is being held by packet 4. Packet 4 needs to go here, but the buffer is being held by packet 1. And packet 1 needs to go here, but that buffer is being held by packet 2. And packet 2 needs to go here, but that buffer is being held by packet 3. And that's why we have a deadlock here. And you can run into these deadlock situations because of your routing algorithm. In this case, the routing algorithm is not XY. Some packets are actually going in the YX direction also. They're taking the Y path first and the X path next. And basically, how do you handle deadlock? Basically, you should ensure that these cycles do not happen somehow, right? This is a bad cycle. There are three fundamental ways of, I think, handling deadlock. If there's a fourth one, again, you can tell me what it is. First, you avoid cycles in routing. Whenever you design your routing algorithm, you ensure that you can never build this circular dependency. And XY routing, actually, I will ask you to think about it if you're interested in this. XY routing has that property. It doesn't have that circular, you cannot form a circular dependency. And how do you do this? There's a seminal paper that I'll briefly describe. You can restrict the turns each packet can take, and XY routing does that, so that you don't have the circular dependency. You can do other solutions. You can avoid deadlock by adding more buffering. Basically, you have these escape paths. Here, for example, you have only one path going from here to here. But if you have an escape channel that enables this packet to escape to some other buffer here, then you can fix this problem. But of course, you need to manage those escape paths nicely. Or, which is a harder problem perhaps, is you can detect and break deadlock. And this is a solution people have not examined as much, at least within the context of on-chip networks. People have tried to do this in the operating system level, because this is an issue when you have threads waiting on the same resource also, right? You can try to detect and break deadlock. You can preempt the buffers. Basically here you can say, oh, I found the circular dependency. First of all, how do you find that circular dependency? And then how do you break it is the next question. What do you take out? Because maybe by taking out this flit, or when I say flit, it's part of a packet. This is the terminology of interconnection network. This flit or packet that's holding this buffer, maybe you're not really preventing the problem. Maybe something else is injecting over here, right? Okay, but these are the three fundamental ways. And this paper that appeared in ISCA in 1992 actually introduced a turn model to avoid deadlock. How do you design these routing algorithms to be deadlock free? Basically, any routing algorithm can be analyzed in which packets can, in the way packets can turn in the network. Like how do they change? How do they go from X through Y or Y through X? Or do you have, what kind of turns do you have? And you can determine the cycles that such turns can form for a given routing algorithm. And you can prohibit just enough turns to break possible cycles. For example, in this case, you may design a routing algorithm that allows this kind of turns of packets. And this won't be deadlock free. You may design another routing algorithm this is the XY routing algorithm actually, that allows this kind of turns. Here you cannot have a cycle, right? This is the turn model. These turns are not allowed, whereas these turns are allowed. And I don't know what this is, but you can read the paper for that. This is actually a beautiful paper too. Okay, one example of oblivious routing is Valiant's algorithm. This is from Leslie Valiant, who won the Turing Award, I think last year or 2 years ago. And I don't have the paper reference, but you can find it You can search for variance algorithm. This is an example of an oblivious algorithm. The idea is the goal is to balance the network load. And the idea is very simple. If you have a network, don't directly send the have a heterogeneous routing algorithm, if you will. Basically, you randomly choose an intermediate destination node and route the packet to that intermediate destination, and then route the packet from there to the original destination. This randomizes the load, assuming that you randomly choose the intermediate destination. And within the source and intermediate destination to the destination, you can actually use XY routing, for example, to ensure that you don't have deadlock. And that's the idea. Or you could use any other routing also. And you can choose multiple intermediate destinations as well, right? The upside is it randomizes and balances network load, so this exploits path diversity really nicely, right? Because you're taking advantage of that path. The downside is non-minimal now, right? Your packet latency actually increases because you're adding this additional destination. You can optimize this. You can do this only on high load. So when do you really need to balance the network load? Maybe when you have high load on the network. Because if you have low load, it makes no sense to increase your latency, perhaps, right? And you can also restrict the intermediate node to be close. So for example, you can divide the network into quadrants like this. And you can, if you're communicating from here to here, and maybe this is not the best example, but maybe if you're communicating from here to here, you can only choose the intermediate node from here, but not from that part of the network. That way you can reduce the latency effect of this. Adaptive routing, this is the most complicated form of routing. It could be minimal adaptive, the network state to pick which productive output port to send a packet to. Productive means packet always makes progress to its destination. Non-productive means packet gets away from its destination. And by definition, if you're minimal adaptive, you're always choosing a productive port, right? Otherwise, you're waiting. And non-minimal adaptive routing is you can misroute packets to non-productive output ports. And deflection routing is one example of this. Basically, whenever you adapt, an adaptation may be, let's say, you get a packet here trying to go over here, but you figure out this path is congested, you can actually send the packet toward this direction, right? That's non-minimal adaptive. I'm sorry? That's right. You need to ensure that that packet actually gets to its destination. Yeah. You need to, and here, whenever you have a non-minimal adaptive routing algorithm, you have the issue of live lock, I think, that will appear here, which is different from deadlock. Okay. So this is aware of local congestion if you have minimal adaptive algorithm. The downside is minimality restricts achievable link utilization because you can only send to a particular link. Not all, many of the other links are actually non-productive, right? You can only pick from the productive links. Whereas here you are more free in which links you pick from. You can achieve better network utilization, better load balance, but now you need to guarantee live lock freedom. What is live lock issue here? Basically, when you send a packet to a destination it really doesn't want to go to, which is not the productive port, then all routers may do the same thing, and this packet may circle in the network forever, right? It may be making progress, but it may not be making useful progress because it's always moving, but it's not going to its destination. So you need to guarantee this. So we'll talk about cheap ways of doing this. One very expensive way of doing this is basically impose a total order in the packets of the network, meaning that every packet is numbered in some way, and all routers obey that prioritization order and ensure that they deliver. They ensure that the oldest packet always gets delivered, and by induction, every packet gets delivered, right? But that total order complicates the arbitration. And also, how do you actually form the total order could be an issue in some networks. But we'll look at very cheap mechanisms to do this in bufferless networks, because bufferless routing is basically a non-minimal adaptive routing, right? If you do deflection routing, that's one form of non-minimal adaptive routing. Okay, so let's take a look at on-chip networks now. So this is hopefully a better picture, which basically shows that you have some processing element that is on chip, and you have a router, And these processing elements could be cores, L2 banks, memory controllers, accelerators. It could be anything. And these routers connect these different processing elements. And this is an example of a 3x3 meshed. These are packet switched. And this two-dimensional mesh is the most commonly used topology, but actually ring topologies look similar, right? You can actually design a ring that looks like this. And the goal in an on-chip network is to primarily serve the cache and memory request, and some I/O requests as well. Traditionally, people have designed these routers, unless it's a ring, and the mesh routers, to have these input ports with buffers. And I'm not going to go into detail, but basically you have a bunch of buffers for each input port. Input port can be from east, west, north, south. And within those buffers you have virtual channels, so that you can you don't have this head of line blocking. The idea of head of line blocking is you partition your buffers, you separate your buffers such that you put different flows to different buffers, and you can arbitrate among them in a round-robin manner, for example, in a simple way. You can have a single buffer, and you can identify the flows differently and do out-of-order scheduling of flows, but that becomes complicated. Here you can have queues, and you can arbitrate from only the head of the queues. This is very similar to actually what we've discussed earlier, right? If you remember out-of-order scheduling versus clustered microarchitectures. Remember I showed you the graph, not graph, but this was your instruction scheduling window, and you had this tag broadcast to figure out what you can schedule. Here, you can put everything into a single buffer, and for different flows, meaning for different source destination pairs, you can schedule things such that you pick different source destination pairs. But you can alternatively partition this window into, in this case, let's say 3, and you can have 3 different FIFO queues, right? And this FIFO queue may have, I don't know, source 1 communicating with some other destination 1, and this FIFO queue can have source 1 communication with destination 3, and source 2 communication with destination 4. And these could be dynamically allocated, of course, right? So that's the idea of these virtual channels. Basically, you partition the channel into 3 instead of having a single monolithic buffer. It's a simple idea.
Each one of these are having a different destination. Is it just based on destination? Or
no, it could be actually extended. Basically, each one of these is a FIFO queue, and it's allocated to a particular packet, if you will. And you could actually still have multiple packets allocated to it, but the idea is to simplify the arbitration, okay, and reduce the head of line blocking. Because if you have a FIFO that is of the same size total and contains all the packets, now you need to pick from the middle of the FIFO if you want to schedule. It's not a FIFO anymore, right?
But that's for destination contention.
That's right, yes. That's for destination. So you could think of this as packet buffers. And they're dynamically allocated. Okay, so you can imagine the complexity of arbitration here, right? It's basically a crossbar arbiter. So to be able to, the control logic, which I'm abstracting away here, it basically needs to determine the route for each packet. It needs to allocate a virtual channel in the next router, assuming that it will win the arbitration. And it needs to allocate this crossbar. So for example, if for each output port, you need to figure out who wants that output port, and you need to arbitrate. So for the arbitration algorithm is for each output port, figure out what is picked to go next. Okay? And the complexity increases as you add more buffers, as you add more input ports, as well as more virtual channels. Okay, and that's the crossbar. That's complex. So let's broadly cover what are the on-chip differences between on-chip and off-chip interconnects. One question that often comes up is people have been designing these off-chip interconnects for decades. What's new here in on-chip interconnects, right? There are some trade-off differences. It's similar to, again, the differences that we covered between multi-core and symmetric multiprocessors, right? The trade-offs are very different. people have been designing the multiprocessors for, again, decades. What's different in multi-core? There are significant differences: latency, bandwidth, resource sharing. And again, you could argue that all of these are true. But power is also an important issue. Power is also an important issue in multi-core. But on-chip advantages, there's low latency between cores. That's different. And you want to maintain that low latency with your interconnection network design. There are no pin constraints, which means that your wiring can be abundant, right, in on-chip. Rich wiring resources, again, because of that reason, as well as there's just a lot of wires. Wires don't consume as much power as off-chip. So on-chip, you have very high bandwidth. And you can also do simpler coordination, right, between different routers. Because you can imagine global control within pockets on chip. Whereas if you're off chip, it may be very costly because you have pin constraints, you have high latency, and you don't have a lot of wires. There are constraints also on chip which actually dictate the design to be different. Here you can enable new opportunities. Here you can, your design needs to be more carefully done. You have a two-dimensional substrate that limits implementable topologies. And you have energy and power consumption, which is a key concern, right? Which is less of a concern if you have off-chip, because you can always scale the power supply, whereas it's a lot more difficult to scale it on-chip. And complex algorithms are undesirable because of these reasons, right? And actually, even though there is a lot of wiring resources, logic area constrains the use of the wiring resources, right? Okay, so let's take a look at this in a little bit more detail. In terms of cost, off-chip, costs come from channels, pins, connectors, and cables. If you look at a supercomputer, I don't know if you follow the high-performance computing community, but they have these top 500 supercomputers. And whenever you look at the pictures of those supercomputers, maybe they've switched to optical interconnects now. That makes things different. But cabling is one of the hard parts of that interconnect design. And all of those cables are, in fact, many of the bugs that are found in those supercomputers and that are fixed are because one cable, the operator, wired one cable to a place that it's not supposed to be wired. So you can take a look at the pictures of those computers at top500.org. So that's a big resource here. Cost comes from cables and reliability of wiring of the cables, perhaps, over there. Whereas on chip, cost is really storage and switches. Wires are actually plentiful. And somebody can do the wiring automatically also, right? Whereas off chip, it's harder. Well, even if off chip, even if you can do it automatically, somebody needs to connect those things. Right? So this leads to networks with many white channels and few buffers, or it may be perhaps should lead to those networks. Channel characteristics are also different. On chip, you have short distance, which means that you have low latency. But also on-chip RC lines need repeaters every 1 or 2 millimeters. Right? But you can also put logic in repeaters. So there are advantages and disadvantages over here. And workloads are potentially different also, right? Perhaps in an on-chip interconnect, you design your workloads to be different. You have a multi-core cache traffic versus supercomputer interconnect traffic. Because the latencies are so interconnects, maybe you don't do distributed caching as much, whereas in multi-core, a lot of the traffic is actually cache and memory controller traffic. Okay, so one motivation of efficient interconnect is this on-chip interconnect consumes significant power, and that'll be I think that'll be most of the rest of my lecture today. People have demonstrated different types of power consumption. For example, in Intel single chip cloud, it's about 10%. In Intel Terascale, it was about 28% of the chip power. An MIT row processor, which was one of the earliest on-chip network prototypes from 1990s, it had 36%. But here, this was very similar. This is a precursor to Tylera, actually. And they had very wimpy processors and fat interconnect. That's where the 36% comes from. So we'll talk about bufferless deflection routing to actually reduce power in die area. But before I go into it, let me talk about some research in interconnects, and then we'll take a break, and then we'll go forward. There are plenty of topics in interconnection networks, I think. This is a very open area, and with any open area, there are lots of people working on it too. So there's an upside and downside. I guess the barrier to entry is very low also. That's another reason a lot of people are working on it. Whereas the barrier to entry in an area where I described earlier, like accelerated critical sections, is very high. I think that's why fewer people are working on it in general. Barrier to entry meaning, I think, the infrastructure issues related to that. Okay, so energy and power efficient and proportional design is a very important part, I think. These are actually, again, biased by my own opinions and my view of the field. Reducing complexity, I think simplified router and protocol designs are critically important because of the differences between on-chip and off-chip interconnects. So maybe I should say novel research topics, because there are a lot of topics that are interesting to look at, but they have been covered in off-chip interconnection networks. And they are easily applicable to on-chip, I think. But this part has not been covered in off-chip interconnects as much. Adaptivity, ability to adapt to different access patterns, similar to what we've discussed in asymmetry. This is a topic that has not been covered as much, and I'm happy to talk about this. Quality of service and performance isolation, while this is very much covered in internet, for example, people have tried to build many quality of service mechanisms that never made it into internet because they changed the protocol, right? They changed the interface. But there's been a lot of interesting work. Well, they made it to the edge parts of the internet, right? For example, if you do video streaming, there are a lot of algorithms that are employed to provide quality of service to different clients that are actually receiving that video. But on-chip interconnect is very different because, again, the complexity. You need to provide quality of service to different applications. Let's say you have a cloud computer, you built this 1,000-core chip, and you're executing applications from many different users, and they're contending with each other. To provide performance isolation, to satisfy the service level agreement of each user, you need to provide quality of service in the interconnect. Or you need to isolate the applications, but then you're not sharing the interconnect. That quality of service needs to be very cheap. And I don't think I'll be able to get to it, but there will be slides in here that you can look at, and one of the readings that talks about how to do this very cheaply. Co-design of interconnects with other shared resources, again, on-chip enables this much better. So how do you co-design, for example, cores and memory controllers and the interconnect together? Maybe they should be aware of each other. Maybe the interconnect should be aware of what packet is more critical to the core. Again, I don't know if I'll be able to get to it, but there are ideas on figuring out the slack of a packet. And you can do that much easily on chip. What is the slack of the packet? Like, how much can you delay this packet without affecting performance significantly? If you can estimate that at the core, then you can inject a priority level into your packet such that the router is downstream, ensure that that packet is appropriately prioritized such that it's delayed just by the right amount, such that it doesn't affect performance. And you could do that much more easily in an on-chip interconnect. Ideas like this become more interesting, I think, when you're on-chip. Scalable topologies to many cores, this is always an issue. And the difference here is something like building a hypercube is very difficult on chip, I think. People have looked at off-chip networks, and hypercubes were perhaps nice and beautiful, but it's going to be very tough to do that on chip. So this is still an important research problem, and my slides cover some of the issues related to this. Fault tolerance, we've discussed this briefly. That's a very important topic also, and doing it with simple mechanisms, again, in on-chip is a difficult part.
What's NOx?
NOx, oh, I'm sorry, that's network on chips. Yeah, one thing I should caution you about people who work in interconnects is there's lots of terminology. I tried to minimize the terminology that I use here, but this somehow escaped. And I think the reason might be because I don't have enough space for interconnects. No, that's not a good excuse, because it seems like there would be a lot of space. But there's a lot of terminology in this area. A lot more than that I already threw at you. Okay, request prioritization, priority inversion, how to build scalable coherence. I think these are very interesting issues also. And if I get to it, I'll talk about some of these. Although I'm not sure, given the speed we have today, maybe we'll just end with energy efficiency. And new technologies are also interesting. They've always been interesting. Optical technology, people have been looking at it from an off-chip point of view. And that's happening in the off-chip world. But it's not clear if it will happen in the on-chip world. That's why it's an interesting research topic, I think. And three-dimensional interconnects is also interesting, especially when you have three-dimensional stacking of chips. So one example, I think, if we pick one of them here, is packet scheduling. If we have time, we'll talk about this also. Which packet do you choose for a given output port? Basically, a router needs to prioritize between competing flits. Flit is another terminology that people have developed. Basically, you don't transmit packets in many interconnects, but you divide the packet into smaller chunks, flits, and you transmit those. Actually, there's a little bit more over there, but that's okay. We can keep this abstraction. Then the question is, which input port do you pick in the next router? Because basically, you're picking this is the output port, and this output port, which input port should you actually pick to transmit to output? Which virtual channel within this input port? And this virtual channel may contain different application packets, or input ports may contain different application packets. Which applications packet do you pick if there are multiple applications that are sharing this? So this becomes an interesting decision in an on-chip network. Whereas in a supercomputer interconnect, this was not an issue much because the application was single, right? Maybe you pick between different flows. There are common strategies that have been used. For example, you can round robin across virtual channels. If you have 4 input ports and 4 virtual channels each, you have 16 things, and you pick the non-empty virtual channel in a round robin way. You can do all this packet first, or you can have an approximation of it. This may be fair in some definition of the word fair, but it's not clear. You can prioritize some virtual channels over others. This basically allows you to actually implement prioritization, some quality of service in the network. Or you can have better policies in a multi-core environment. You can use application characteristics, for example. You can divide the applications into latency sensitive versus bandwidth sensitive and prioritize latency sensitive applications. And if I have time, I'll discuss some of these issues. Or you can design policies to minimize energy somehow, or minimize the slack of the system. Okay. Maybe we should stop here for a short time and take a 5-minute break. For graduates.
For both undergraduates and for high school.
Oh, for high school.
The high schools are also just studying the clusters, and they are trying to decide whether they should write this department in the university and section.
Oh, okay. Hopefully you'll get the good ones. Okay, we've covered a lot of the basics of interconnection networks. Now let's take a look at some research. I think given that we have a little bit over an hour left, we'll probably focus only on bufferless routing on-chip networks. I think this is a very exciting area for me, and there's a lot that can be done. So if you're looking for research ideas, topics, and this topic excites you, I think I'd be happy to talk about this. So when we started, this is the original paper that we wrote on this, a case for bufferless routing in on-chip networks. People were, I'll give you a little bit of background, people were overwhelmingly considering using buffers in the network, in a multi-core network. And this was interesting to us. So this paper introduces a lot of problems, but the implementation in this paper also has a lot of problems that we later solved, hopefully. Hopefully solved. And even if they're not solved, it's still research, right? So I've already talked about on-chip networks. There are many design goals in on-chip networks, and power and low energy is one of them. And I've already talked about why this is an important point. At the time, there were chips that had 30% of their power that are consumed in the on-chip network. And this is actually an interesting paper by Shekhar Borkar, 1,000-core chips, that estimates that network on chips will consume about hundreds of watts in the future. Although that's probably not feasible, right, if you scale the current trend. So there were many approaches in network on chip design people have looked at, and these are again research topics. I'm not going to go into that. Network topology, flow control, virtual channels, quality of service and fairness mechanisms, routing algorithms, router architecture, broadcast and multicast support. And all of these actually assume the existence of buffers in the network. Maybe all is quite strong, but most of the overwhelmingly large majority at the time assumed the existence of buffers. And this is probably still true, by the way. But at least we have a fraction. We have carved out a space that looks at bufferless networks. So a typical router looks like this. We've covered some of this. This may look nicer. But you have a bunch of virtual channels for each input port, and you arbitrate for each output port. And that's, again, red. And there's complexity associated with it. Certainly, you have this buffering complexity. And you have actually, you need to do flow control. What if you're trying to inject a packet into this hardware router, and you cannot? Somebody needs to tell you that, right? You should not inject a packet. So basically, the router, upstream router that's trying to send packets to this port needs to know whether there are virtual channels available here, which is not that easy to communicate if you have lots of virtual channels. And that needs to happen here also. So when multiple packets come here, and these are different colored, but, oh, okay. They're both red. That's good. So these both need to take the same output port. And the router arbitrates and, let's say, picks that virtual channel. Buffers are an integral part of existing routers. So you need to do this arbitration somehow. So what is the advantage of buffers? The upside is these are necessary for high network throughput. Buffers increase the total available bandwidth in the network, right? So this is a very common curve that you will see. This is the injection rate. How much load you put on the network, how much injection that each node does with some metric here. And the y-axis is the average packet latency. And if you have lots of small buffers, your latency shoots up at some point. And this point where the latency shoots up is called the saturation throughput. Basically, your network saturates at this point. It goes to asymptote. It cannot support higher load injection than this point. And that's with small buffers. If you increase your size of buffers, the network can support more injection because you keep pushing stuff into the network. And if you increase your buffers even more, you can support more injection. As a result, your network latency, you can cover a broader range of network injection rate as you increase your buffering, right? While keeping the latency low. So this is the upside of buffers. But there are many downsides. They consume significant energy and power. They consume dynamic energy when you read and write into the buffer. And they consume static energy even when it's not occupied, right? And these add complexity and latency. You need to have logic for buffer management, for virtual channel allocation, and flow control. Credit-based flow control. We'll see that bufferless networks require flow control as well, but in a different way. These require significant chip area as well. For example, the one prototype chip that had on-chip networks from UT Austin showed that input buffers occupy 75% of the total on-chip network area. Now, you take this with a grain of salt. This may not be optimized buffers. Still, 75% is a very large number. So we would like to try going bufferless, basically. Get rid of these buffers and rethink the entire network design. Now, this requires rethinking a lot of things like quality of service. How do you do quality of service in a bufferless network? And I think that's an unsolved problem, which is a very interesting research area. But how much throughput do you lose? How is latency affected? Basically, buffers and no buffers. What is the saturation throughput you lose? And how does latency get affected here and here? And up to what injection rates can we use bufferless routing? And are there realistic scenarios in network on chips where injection rates do not go beyond this part such that we can support buffers? Right? Maybe some applications do not communicate that much, and designing a bufferless network is a good idea for those, right? So can we achieve energy reduction? If so, how much? And can we reduce the area complexity, ... so that we can add more communication, add more computation and memory elements? Right? So the idea of bufferless routing, I think I've already given you this. Basically, when two packets need to use the same output port, in a buffered network, you buffer one of them. In a bufferless network, basically, you send one packet to a direction it doesn't want to go to. And we've already talked about this, and that's the hot potato, I guess. So basically, we're going to eliminate this buffering logic and all of the logic associated with it and the credit-based flow control. Instead, we're going to replace it with two things. First, we're going to create a ranking over all incoming flits. And we're going to do port prioritization. For a given flit, and flit, remember, is a part of a packet. In this ranking, we find the best free output port and apply to each flit in the order of ranking. So the flit that's ranked highest will get the output port at once.
So do you assign a bit for the prioritization for the flit?
It's more than a bit, actually.
Basically, you put some sort of, let's say, identification.
That's right.
Okay.
That's right, yes. Basically, you rank the flits and say, this is the highest, this is the lowest. And in that order, you assign, the flits get their output ports they desire.
Okay.
So the highest ranked flit always gets the productive output port.
So you get longer packets.
That's right. So you get longer critical path because of this. And we'll see that that's a problem, actually. That's one of the issues with this paper. This was more of a, yeah.
This will also increase the energy.
Doing this, yes. But we're going to fix this problem, yeah. So that is the problem with this paper. It's always good to criticize your own paper first and others' papers next. So this was more of a big idea kind of paper. Basically, the big idea is we should reconsider the design of a network. But this glossed over a lot of the implementation issues. And this is a big implementation issue that you point out. And hopefully I'm going to try to solve that issue soon. Okay, so let's go through this relatively quickly because I'm going to solve this issue in more detail. Basically, each flit is routed independently. We have oldest first arbitration. And the goal of oldest first arbitration is to ensure that you have a total order. So to eliminate live lock, right? Because if you keep sending packets to a place that they don't want to go to, you need to ensure that packets actually make progress to their destination. And if you ensure that you have a total order in the packets, you can actually ensure that the network makes progress. And basically, we have oldest first ranking in the flit ranking. And port prioritization, we assign flit to the productive port if possible. Otherwise, we assign to non-productive port, meaning to a port that takes the flit away from its destination. And eventually, all flits will be assigned, will be the oldest flit. Eventually, a flit can become an oldest flit, and it can make progress. So topology, so where can this be applied? It can be applied to most topologies, not all. Because you need to have, basically you need to have number of output ports. Actually, this doesn't look good. I don't know why. But the number of output ports should be greater than or equal to the number of input ports, right? If the number of output ports is less than number of input ports, then you cannot do this. Because you have nowhere to throw at least one packet in that case. So, but this is true for mesh, torus, hypercube, and trees, many networks. And every router needs to be reachable from every other router. Otherwise, you need to restrict the routing policy that is described here. Flow control is completely local. We're going to fix this problem also. But at least for the buffering, there is no flow control because there are no buffers. But injection policy, you're going to inject whenever the input port is free. And we will see that this actually causes starvation issues because what if your input port is not free, right? Input port meaning free is you have some link that's free, basically. This has no deadlocks because every flit is always moving. This has no live locks with oldest first ranking, but we'll see that that's a problem because this causes the long critical path in the router. So you could actually use this with buffers also, but that's more deflection routing with buffers. You can have buffers, but you use buffers opportunistically. Basically, no buffer is an extreme end of a continuum. Whenever a buffer is full, its first flit becomes must schedule. In that case, and whenever a buffer is not full, and these must schedule flits must be deflected if necessary. Right? Whenever a buffer is not full, you can use just normal arbitration. Yes.
Flit is usually associated with the wormhole routing. Flit is so tiny, there is no header attached or destination address. But I think you're using flit in another way. It's kind of fine granularity packet.
Yes, absolutely. Right? Absolutely, you're right. You're right.
No
so
where to go, so independently you can send.
That's right. So in this case, in this routing algorithm, you're absolutely right. We're actually treating a flit, we're actually attaching a header to a flit. Now in the paper we discuss how to combine this with wormhole routing also. That becomes a little bit hairy, but we do have a mechanism that combines it with wormhole routing, and there the flits don't have headers. But now you need to have a mechanism to be able to break the packets because you need to somehow arbitrate, and that becomes that's the hairy part. But for this flitless, flits are actually smaller packets. Okay, so you can see the paper for this. Actually, there is a paper that used deflection routing with buffers. It's called the chaos router, which is an interesting router design. I think it's by Larry Snyder's group. was ISCA 1991, I think. If you're interested in that, you can take a look at that. Okay, so what are the advantages and disadvantages of bufferless routing? Advantages: no buffers, purely local flow control. We'll revisit that for the protocol level. Simplicity: no credit flows, no virtual channels, and simplified router design at some level. No deadlocks and live locks, assuming you design your routing algorithm nicely. And it's adaptive. Packets are deflected around congested areas. And you get adaptivity naturally, right? There's no need to design some other thing. Basically, whenever you have congestion, you have this nice behavior that packets get deflected around that congestion, and you can utilize all of your links dynamically. You get router latency reduction also. I'll briefly describe that, but I won't dwell on that a lot. And you get area savings. Disadvantages: you get increased latency, reduced bandwidth, increased buffering at the receiver. We'll look at that again. You have header information at each flit. This is what you mentioned. Oldest first arbitration is more complex, and we're going to try to solve this. Quality of service becomes more difficult. So I'm going to solve some of these problems in later. So what is the impact of energy? We'll take a look at that. But how can you reduce router latency? Very briefly, by getting rid of input buffers and virtual channels, you can actually reduce some of the stages that are required in the router. So a modern virtual channel router looks like this. Basically, you write to a buffer, you compute the route of the flit, and you allocate a virtual channel, and then you allocate the switch, which is the crossbar. And then there's a stage where the packet traverses the switch, which is the crossbar traversal. And then after that, it goes into the link. Basically goes through the output port here. And you could actually have something else we'll discuss here. In the baseline router, you can design actually a 3-stage router by overlapping some of these latencies. And this is speculative. You can actually design a speculative router. Basically, at this stage, you speculate that the router will actually get the switch. The packet will actually get the switch. And you can design the router that way. If the packet actually doesn't get the switch, doesn't get the switch to be allocated to itself, then you need to back up and reschedule the packet. That way, you can reduce the router latency to 3 and in fact to 2. With a bufferless router, you could do this. You could have route computation and switch traversal. That's pretty much it, actually. Well, you need to do the ranking somewhere over here, of course. So you could actually do at the cycle level, latency to be 2. And if you actually can do this much more aggressively, you can reduce the latency to 1. And this is going to be tougher, but what you can do is you can do a look-ahead link traversal. You can actually send, whenever you do the ranking and the arbitration before doing the switch traversal, you can send via some separate links to the next router that, oh, I'm going to send this packet to you with this information, with this priority. So start doing the route computation while this packet is within my switch. So you're basically sending a look ahead to the next router saying that in the next cycle, I'm going to send this packet to you. You could do this actually in other routers over here, and we're assuming that you do that over here. This was proposed for baseline buffered routers. But this way, you can actually reduce the router latency to 1 cycle. This is an extreme, of course. It's tough to build this one, especially at higher frequencies.
You assume that route computation takes equal time in all of these implementations.
So I'm not saying anything about frequency here. That's right. I'm saying things about stage level, cycle level. assuming you could, you're running at a frequency where these cycles are, where you can do this in 3 cycles, 2 cycles, 1 cycle. Yes, but we're going to fix that problem. We're going to try to make this. So what you're getting at is this is much more complex here, this route computation and ranking. And that's absolutely true. And we're going to fix that problem, basically. OK. So disadvantages, there are extensive evaluations in the paper and in other papers also. Let's take a look at overall results a little bit. Basically, I'll refer you to many of these, to the paper for many of these. But we evaluated this with many real applications. You could argue that these are not necessarily representative for everything, but we have Windows desktop applications and some spec applications, and homogeneous and heterogeneous application mixes and some synthetic traffic patterns as well. And these are the networks. We looked at this kind of networks, and the processor model is this one, which is an aggressive processor model. And this is evaluation methodology. If you're interested in that, you can read the paper for more detail. And there are comparisons against non-adaptive and aggressive adaptive buffered routing algorithms, dimension order routing, minimal adaptive routing, and a routing algorithm called ROM, which is based on Valiant's algorithm. Okay, so let's take a look at synthetic traces first. So this is kind of bad news if you look at this. This is uniform random injection. Basically, every node injects at this injection rate uniformly and to a random destination within the network. And if you look at this, this is a minimal adaptive routing. So it can support approximately 0.5 flits per cycle per node, which is pretty high. And if you look at this, these are different flavors of bufferless routing, and some of them are wormhole routing based, some of them are what I described. But basically, they saturate around 0.29 or so. So the saturation throughput is much lower over here. So you get significantly lower performance for this. But it turns out most benchmarks don't need this much saturation. Most real applications we've seen don't need this much saturation throughput. A lot of them are closer to the bottom side. And this is actually an observation many other people have made also. It wasn't only us. Many other people saw that the injection rate into the network in many core networks is very low. That's why they try to turn off links, do other optimizations that reduce the utilization of the network. So this is one example. Milk is one actually intensive application. We're assuming perfect caches. This is perfect L2 cache, such that all of the traffic stays local. Because once you start going to memory, memory latency dominates in some benchmarks, some workloads, and then your network becomes underutilized anyway. So if you look at this, these are different algorithms, and their performance is the same pretty much for an 8x8 network. The only difference over here is, basically the takeaway here is the performance is very similar for this homogeneous workload. So that's what we've seen. So very little performance degradation with bufferless routing. And with router latency 1, you can actually outperform the baseline if you can do that. And assuming that you can build a router with this frequency. So what about the impact on energy? So you get significant energy improvement. These are the red parts. Those are the buffer energy that you can reduce. And this is the distribution of energy in a router for the, let's take a look at the 8x8 network over here, dimension order routing. So most of the energy is actually the router itself, arbitration, and buffering. And link energy is relatively low. That's what we've seen because the injection rate is relatively low. Basically, most of the buffer energy is reduced. We still have some buffer energy because we need to buffer some small parts of the flit. Okay, so basically, injection rates are not extremely high on average and the main reason is network is actually self-throttling. These processors, at some point, they need to stall. They do not keep injecting into the network. And the L1 caches actually filter the traffic. And for bursts and temporary hotspots, the bufferless routing uses network links as buffers. So you get some adaptivity benefits because of bufferless routing. So there are some further results, but I think I'll get rid of these right now and we'll take a look at this one. Basically, this was the overall average that we've seen. If you have a perfect L2 cache that's distributed such that network traffic remains local and the network is utilized as much as possible, the network energy reduction on average was about 39% and system performance degradation was 0.5%. In the worst case, we saw that network energy reduction was 28% and system performance degraded by 3%. I think we were quite optimistic. We'll see other results later on. With realistic L2, the reductions are even better over here. So with realistic L2, you actually get more network energy reduction because most of your bottleneck has shifted to main memory now, and system performance degradation becomes even smaller because network is not as big of a bottleneck. So this, I think this, one way to interpret these results is perfect L2 is similar to those benchmarks that are cache resident. So you would like to be cache resident. Realistic L2 is for those workloads that are more memory bound. And these are actually some results with the dense networks. So actually, I should say that this is a sparse network where you have smaller number of cores. Here you have more number of cores. Here the degradation is higher. So this is similar to the results that I'll show you later. Basically, the network energy reduction on average is still good, and system performance degradation is a little bit higher because you have more nodes, you have more congestion in the network, more load on the network. In the worst case, you can actually get significant performance degradation with perfect L2. But with a realistic L2, it reduces.
By the way, how many nodes do you mean by saying dense or sparse?
Yeah, so I think,
10 or?
yeah, this is 16 and this is 64, I think. Yeah. But this, I think I'll say that the results that we have in the next work that I'll describe are more representative. So this reduction will go higher, to 50% or so.
Do you mean 4x4 and 8x8?
Yes. Mm-hmm.
Too good to be true. I mean,
Yes.
L2 seems far better than perfect L2, but you're actually shifting problem to the main memory.
That's right,
side.
yeah.
Isolating that part only, it seems good, right? Is that correct?
So yes, here, this is a more realistic system, right?
Traffic will be less
That's right.
shifted to the main memory side.
That's right.
Therefore, it seems so good, right?
Here, yeah, that's right. More traffic actually goes to memory,
Yeah.
which means that you're more latency bound than
You
memory.
ignore that.
That's right.
I mean, the overall performance is not that good, actually.
Yes, so,
They
that's
catch
right.
traffic, isolated performance.
This performance is higher. That's what you're saying. Yes. But here you basically keep going to memory, so a network becomes not much of a bottleneck because memory latency is on the order of hundreds of cycles, right?
Relief, but there's quite a problem on the other side.
That's right.
Networks. The
The main memory side, exactly, yes, exactly. So I think going forward, it really depends on the application, actually. Some applications are cache resident, so you'll see this kind of behavior. Some applications are not cache resident, so memory is the bottleneck. Okay, so these were the results that we've concluded at the time. But basically, you have significant energy savings, area savings that I did not talk about, but you get 60% network area savings with this. You have simplified router and network design, and performance slowdown is minimal. Performance can even increase. This is all assuming that the simplified router is actually true, right? And you can run it at a high frequency. So we're going to take that and hopefully try to fix it. So we've tried to make a strong case for rethinking the network on chip design. Now let's take a look at some of the problems. And this was what we thought was future research at the time. Support for quality of service, which I think is still important. Like, how do you support quality of service in a deflection routing network? Different traffic classes, energy management, and maybe how to simplify the router. Let's take a look at that. So we realized that deflection router actually is much more complex when you try to implement it. And I'm going to skip this because these are actually, our goal was to obtain, so there were unaddressed complexities in the router. And there are two things. One is the long critical path that we've discussed, and I'll discuss why you have a long critical path, and large reassembly buffers. Basically, we would like to obtain these large benefits that we've seen earlier while simplifying the router to make bufferless routing practical. So there are two problems that bufferless routers must solve. They have to provide live lock freedom. A packet should not be deflected forever. And they must reassemble packets upon arrival. With a wormhole routing, it's buffered wormhole router, it's much nicer because packets come nicely together. Whereas in a bufferless router, packets can come anytime, right? Because they're just deflected everywhere. So you need to have enough buffering somehow. So this is a difference between flit and packet, by the way. That should have come much earlier, I think. Okay, so how does a bufferless router look like? Basically, you have this deflection routing logic, and that goes into the crossbar. This is the injection from the local node, and this is ejection into the local node. So the local node needs to reassemble these pieces of the packet, and then take the full packet, let's say a cache line, and send it to the cache. The first problem is here, and the second problem, packet reassembly, is here. Let's take a look at the, well, how did we solve this first problem first? Basically, we sorted the flits by age and then assigned an age order to output ports, right? It turns out this leads to 43% longer critical path than a buffered router, which is pretty high. The second issue is reassembly buffers must be sized for the worst case. And if you look at the worst case, which I'll show you, it could be 4 kilobytes per node. And I'll show you the worst case later on, which could be pretty high in a 64 node system. And it becomes much worse in a 1,000 node system, right? Let's take a look at the first problem. So what stops a flit from deflecting forever? Basically, we timestamp all the flits, and all the flits are assigned their desired ports. So the goal here was a total order among flits, which means that you guarantee progress. This flit is guaranteed progress, and new traffic is lowest priority, but there's a cost to this. So how do you actually implement this? So a router must sort flits by age. Basically, you have a long latency sort network. Right? Now we're going into the design of the router. And this is, if you have 4 flits, basically you have 3 comparator stages. This is what a sort network looks like. There's actually a beautiful paper, Sorting Networks, that talk about different sorting networks. That is relatively old. So age-based priorities are expensive. So after sorting, after this, flits need to be assigned to output ports in priority order. And that becomes difficult also, because port assignment of younger flits depends on that of the older flits, right? Because you have the sequential port allocation. Let's take a look at why that is the case. Let's say you sorted these flits. The first flit, that needs to get its productive port. So it wants east. And it's granted east because that's the highest priority flit, and that's not allocated. Now east is allocated, which means that this port allocator says, oh, north, south, west are available. Now the second port allocator can allocate only from that. But this wants east also. In this case, second port allocator says deflect this flit, and it's allocated north. Now this next port allocator needs to know what's already allocated, right? This wants south, and south is not allocated, so it's granted. And only west port is left, and this fourth port allocator sees that this flit wants south, so it's deflected. It has to go to west, right?
Here you assume that the flit will still be transferred to the east while you are processing the fourth flit.
No, this all needs to be done in parallel. Yes.
Synchronous?
Sequential?
Yeah, it is sequential. That's why you get a long critical path.
But in one cycle.
In one cycle, that's right, yes. In one cycle.
Otherwise, if in the meantime, east can be available and fourth packet or flit can also be granted east.
That's right, but that leads to a very different kind of router, perhaps. We haven't considered that, but that won't buy you much, right? Because you still need to go through this arbitration, and you need to design the network in a different way, right? Okay, so this is basically a sequential allocation, right? Basically, the age-based priorities are expensive because you need to do this priority sort, and this port allocation, your critical path is this way, basically. And we've implemented this in RTL and found that you get 43% longer critical path. So we want to reduce this. Is there a cheaper way to route while guaranteeing lilac freedom? And the realization comes from asking the question, what is really necessary for lilac freedom? So what is really necessary is, you don't need this total order. That's the realization. It's enough to pick one flit and prioritize it until it arrives. That way you guarantee the progress of this flit. So we're going to call this the golden flit. And we're going to distinguish only between the golden flit and everything else in the world. So you have a partial order now. There is no ordering within this cloud, and there is only ordering here. And ensure that any flit is eventually picked from this cloud to be the golden flit. That way you guarantee live-lock freedom. Right? And this, so what does golden flit routing require in this case? So you need to ensure that all the routers obey this, recognize this golden flit. Right? Basically, you only need to properly route the golden flit. Let's assume that we've selected it. Now you get rid of the priority sort, and you get rid of sequential allocation also. So how do you actually route the golden flit in a 2-input router? Basically, you pick a winning flit. If there's a golden flit, 1 bit, you check, then that's the winning flit. Otherwise, you randomly pick one of the input ports. Right? And you steer the winning flit to its desired output and deflect the other flit. Now you can build a golden flit always routes towards its destination because you always prioritize it, right? It's always a winning flit if it exists. Now you can actually make a 4-input router this way. Basically, we take whatever I described here and connect it as a permutation network like this. Now your deflection is a distributed decision, right? Northeast ports, southwest ports, and you can actually connect these in different ways. This is to minimize the deflections. But let's take a look at how this operates. I guess the colors are kind of bad here, but that's okay. This is the golden flit. It happens to be yellow. And these are the destinations of these different flits. Unfortunately, I think this is the yellow part. Okay, so let's take a look at decision here. None of them is golden, so randomly this node picks one of them. And north goes to its destination, and its destination is here. If you look at this, the red needs to go here. Here, it's the golden flit, so it has to win based on the design of this. So it wins and it goes this way, because it's not going to go up there, that way. Now this is what happened. And this one wins randomly again, and they go to their destination. So I was lucky, I guess, in this winning, right? Because it was their ending. Actually, we're going to fix this problem also in the next work. But if you have one, well, anyway, you could do better. Here, again, golden flit wins. So golden flit definitely goes to its destination, and this is deflected. So now deflection arises in a distributed way, and you ensure that live lock freedom is provided. As long as every flit can become golden, it can always reach its destination. Do you want to change? Okay.